Which of the following carbons has no hydrogens directly attached? And there should be exactly one best answer. Good, so hopefully this was fairly straightforward. Hopefully you've been practicing your line angle drawings. And again, I think I've made this point. If you don't like using line angle drawings, if you'd rather, use condensed forms, it's fine. I think with something like this, I imagine most of you will at least draw the six-membered ring as a line angle drawing. But whatever your individual style of drawing structures is, and everyone's will be different, and that's fine. All I ask is that if you see line angle drawings, you understand them and can interpret them correctly. So hopefully you came to the conclusion that carbon D, which has 4 single bonds coming away from it, that one's got to be the one that has no hydrogens. B and C each have 1 hydrogen that's not shown. E is, of course, a methyl group, and A has 1 hydrogen not shown. So I think the best answer is D. Yep, and I will mark it accordingly. Good. Next and last question. Which of the following is 3-ethylhexane? Would be helpful if you could see the whole structures. And unless I've completely lost it, which is always possible, I think one of those is definitely the best answer. And remember, it's probably not gonna be accurate on the Reef webpage. I still have to get in there and finish the grading and take care of the attendance. There's always a couple of excused absences I need to take care of, all this type of thing. And then I'll import it into my own personal grade book and make sure everything looks correct, and then upload that to eCampus. And I'll probably do that this weekend for the latest grades from this week. If at that point you see something wrong on eCampus, please let me know. Certainly what you see on eCampus will supersede anything you might see on the Reef website. I almost want to tell you guys not even to look at the Reef website. I just feel silly saying that, but it's very tempting for me to say that. But certainly go with what it says on eCampus rather than on the Reef website. All right, looks like we're holding steady at 95. Very good. Well, so we need to find something that has a carbon chain of 6 carbons. 1, 2, 3, 4, 5. That's no good. This one I think also only is 5. This one is 6, no matter which way we count. Here's a chain of 6, so that's fine. I don't think I can get anything longer on D than a chain of 5 carbons. So that narrows it down to C and E. Make sense? So we just need to find something that matches the description. And 1, 2, 3 looks like you only get the points if you only get the point for this question if you're correct, but you'll still get at least 8 for attendance. I'll get that later. Most of the points are always going to come from attendance. And of course, some days you just get all 10 for attendance. But I think with this one, 1, 2, 3, this looks to be an ethyl group, CH2CH3. So I think that's the best answer. This guy, I think, would be 3-methylhexane. So I think the best answer is C. Everyone see how I got that? Yep, and overwhelmingly the class thinks C also. So like I said, I'll make sure you all get the 8 attendance points too. But that's pretty much it for now. Good, and with that I think we can finally dive in. Whoops, I broke the thing, I always do that. I think we can finally get started with cyclohexane and the structure of cyclohexane. So we went over the smaller cyclohexanes and the smaller cycloalkanes, and there we said that cyclopropane and cyclobutane are quite strained. They have a great deal of angle strain, which is also called ring strain. There you go, 2 names for the same thing yet again. Cyclopentane is almost strain-free. Not quite, but pretty darn close, because now the ring has enough members in it, it's opened up enough that we can get pretty close to that ideal bond angle of 109.5 degrees. With cyclohexane, we've gotten rid of all angle strain and also all torsional strain. I have a model of the compound over here. Oh, you can't see that just yet, but we'll get the document camera on pretty soon. By which you can see, for instance, that all of the hydrogens are perfectly staggered. But cyclohexane is not planar. Now, sure, you can you explain how you knew to look for a chain of 6? Because the word hexane was in the name. That's how I knew to look for a chain. Oh, people are talking about it. Yes, looks like Cameron was right. Okay, so certainly you can draw cyclohexane like this, and it's not wrong. It just doesn't show the correct shape of the molecule. You'll know what to do based on what the question asks you to do. Often this type of drawing is perfectly fine. One quick side note, remember cyclohexane and benzene are completely different critters. Yes, they both involve a 6-membered ring, but they're entirely different compounds, totally different reactivity and behavior. So please don't just memorize that it's a thing with a hexagon. You need to interact with the material so that you understand it better. Good, so in its most stable conformation, cyclohexane adopts what's called a chair conformation. And part of this material is knowing how to draw cyclohexane in the chair conformation. So this material is included in the exam material. And as you can see, what we're really doing, I should probably lead also by saying, we're using sawhorse projections here. So that's why there are no wedges and dots. By convention, we use a sawhorse projection when we're drawing cyclohexane in the chair conformation. And I guess they call it that because one can imagine, you know, putting your butt here and then your legs go here and you can lie back with your head over there. So it sort of looks a little bit like a chair if you kind of squint at it. But in any case, at room temperature, there is a rapid equilibrium between 2 different chair forms that are equivalent in energy. And we'll go over that ring flip conformation. That's something that in my experience, that is one of the things that needs the most explanation. And cyclohexane is C6H12, so there's 12 hydrogens. And as you can see, we've got 3 hydrogens that point straight down, and 3 also that point straight up on the other side of the ring. We call those positions axial positions. And then the remaining 6 hydrogens that stick around the equator, around the periphery of the ring, we call those equatorial hydrogens. And if there were other groups replacing the hydrogens, those would still be axial and equatorial positions. And we could say, this group is axial, that group is equatorial. So that's how that phrase is used. But please note that cyclohexane, no matter which of these chair forms it adopts, has at all times 6 positions that are axial and 6 positions that are equatorial. Please also note that 6 of these are up. So for them, we would use a wedge bond if we were drawing more this type of structure. And the easier ones that are to see that are up are, of course, the axials. But there is also such a thing as equatorial and up. So this one is pointing up a little bit, we'd use a wedge bond for that. This one is pointing up a little bit, we'd use a wedge bond for that. That one's pointing up a little bit, we'd use a wedge bond for that. And if you're having trouble telling whether a particular equatorial position is up or down, what you should do is find the axial group on that same carbon. I think you'll agree that hydrogen is most definitely down. There's absolutely no question about that, right? You see what I mean? So that means that the equatorial group on the same carbon must be up. So every carbon has 1 axial and 1 equatorial position, and every carbon is 1 up and 1 down position. And we're going to talk about this more the next time. That's one of the hard things about cyclohexanes, is up and down do not correlate with axial and equatorial. Up can be either axial or equatorial. Down can be either axial or equatorial. And we'll talk more about that the next time. That's something that I find needs extra explanation. That can wait until Monday, though. So anyway, this is the most common way of drawing cyclohexane chairs, something like that. And today I'm basically hoping to get through unsubstituted cyclohexane and then also consider what happens when you replace one of the hydrogens with some other group. That's going to affect the equilibrium quite a bit. And that happens to be because of, I think we would need to call this one steric strain, because I don't think these follow the definition of eclipsed exactly. But there is a type of steric strain that is involved when groups other than hydrogen are axial. And so you'll find the molecule tries to avoid those conformations, if possible. It's not always possible. Now, yes, there are other conformations of cyclohexane. There's something called a boat conformation that you very seldom see. I can even draw that for you. Something kind of like that. It's very rare. There's quite a bit of steric strain between those two hydrogens, which they call flagpole hydrogens, which is kind of cute. But you can imagine if you put a sail on this thing, it would kind of float on water. So they call that the boat conformation. And again, it tries to avoid that. There's also something called a twist boat conformation that relieves that interaction a little bit by bending sort of the floor of the boat, by sort of kinking that so it's out of plane. And that relieves that a little bit, but it's still higher energy than the chair conformation. The chair conformation is the lowest energy conformation for cyclohexanes. Yes? Did I forget an H? Let's see. Oh, you're right. I did forget the H's. Shame on me. Yep, they're still there. That's the axial one, and that's the equatorial one. Thanks. Okay, so yeah, should be C6H12 for both of them. So as I said, this equilibrium that you see here is very rapid at room temperature. And by the way, this really is an equilibrium. So here we really do have things flipping back and forth. This is not a resonance situation. You'll notice I'm using the equilibrium arrow. And those two chair forms, and we're going to use models and so forth to help us see how to get from one to the other. But those two chair forms are different, but they're equivalent in energy, of course, because there's no difference between them structurally. They both have 6 axial and 6 equatorial hydrogens. There should be nothing favoring one of these over the other. It's when we start replacing hydrogens with other groups, that's when it gets real. Like I said, my goal for today is at least to get as far as considering monosubstituted cyclohexanes. See where was, oh, so this equilibrium, as I said, is quite rapid. Now, this equilibrium as shown with just unsubstituted cyclohexane, of course, the equilibrium constant for this will be 1 because these two are equal in energy. So that will not be the case necessarily, at least when we start substituting cyclohexanes, and it becomes especially interesting for the disubstituted cases. Good. So I think that's about as far as we can get for that. What does the so-called ring flip conformational change then that we use to get from one chair form to the other? We call that a ring flip conformational change. And I think I have some diagrams on that in the class notes as well. One thing we need to be very clear on is we're not just flipping the ring over like a pancake. That's not how this works. It's instead a conformational change that involves rotating around all of the carbon-carbon bonds, at least as far as we can, right? We can't rotate anything like 360 degrees because they're attached to one another. It's a ring. But there is still flexibility in this molecule, and I'll show you that in a moment in the model. And let's see. In a typical ring flip conformational change, I'm going to show you first of all schematically kind of on this drawing how that works. And then I think we would be best served moving on to the models. So if I just numbered these carbons, I'm doing so arbitrarily. 1, 2, 3, 4, 5, 6. The ring flip conformational change involves grabbing hold of 2 opposite carbons. We could say carbons 1 and 4. And what we're going to do is pull carbon 1 up. That's not a mechanism arrow, obviously. And we'll push carbon 4 down. And as a result, carbon 1 will move up here. So this is now going to be carbon 1, 2, 3, 4, 5, 6. The reason I'm stressing all this is because we'll need to know about that in order to draw chair conformations that are a little more difficult, maybe when the cyclohexane is substituted. And you could, of course, go back to where you started by grabbing carbons 1 and 4 again. So we're going to pull carbon 4 up and push carbon 1 down. That will go up here. That will go down there. And then you get back to where we started. So I think this will become somewhat clearer when we skip to the models. So we'll go back to that drawing in just a moment. But like I said, I think this is a place where models really can help us. I just hope I can keep the model on screen and reasonably in focus. So not that camera, but this one, I think. Yep, there we go. So there's our model of cyclohexane. And you can see, I think, as I turn it, that this molecule is, as I said, not planar. So I've put in the axial hydrogens as green, and you can see they're extending straight up or straight down. And I've put in the equatorial hydrogens as white. So, but the molecule is not planar. And so this is the chair conformation. That's the one that's the most stable. So what happens when we do a ring flip conformational change? Just trying to keep everything on the screen. Well, again, we're going to grab one carbon and grab another carbon in the opposite side, and we'll pull this one up and we'll pull that one down. So this is something where begging, borrowing, or stealing, well, don't steal. Begging, borrowing, or borrowing or buying, I guess, molecular models can come in handy. People have asked me if I recommend this particular kit that I'm using. My one-word answer to that is no, because this is the special teacher's kit. So it's bigger and there's extra doodads in it. And even then, it was not expensive. I paid maybe 40 bucks for it on like eBay or Amazon, one of those. But you don't need the teacher's kit. They make student ones that are maybe 15 or 20 bucks. And that's the type that I would recommend. I do like these ones with the little plastic balls and the plastic bonds like this. I just think they make things easier to visualize that way. So, but again, you can grab any two opposite carbons you like, and you'll pull the lower one up and push the upper one down, and that's what the ring flip conformation looks like. So you can see it's really rotating around all of those carbon-carbon bonds, and the entire molecule inverts in a sense. So that's what's involved in a cyclohexane ring flip conformation. Reason you need to know about this is cyclohexanes show up a lot in nature, and it helps to know something about how that molecule behaves, even with other groups on it. So one other thing that I hope you all noticed, I think you all noticed it, anyone notice anything regarding the axial and equatorial positions after a ring flip? And again, nothing up my sleeve. My hands never left my wrists. What happened to the axial and equatorial positions? Yeah, they switched. And that's always going to be the case. Every ring flip conformational change interconverts the axial and equatorial positions so that what had been axial is now equatorial, and what had been equatorial is now axial. That's always going to be the case. So, so far then, that is more or less the nature of cyclohexane. Let's now switch back to where we were. And I think that puts us in a good place to consider monosubstituted cyclohexanes. I lied. Let's do one quick thing first, because you might need it for lab, for those of you that are in lab. But other questions before we do that? Yes. Glucose is the question is about alpha and beta glucose. I don't expect you to know which is which at this point. We'll eventually learn that in chapter 25 or 4 next term. But the reason you need to know about cyclohexanes in order to answer questions about glucose is just like cyclohexane in a way, except, I failed at that, except that one of the CH2s is replaced with an oxygen. And then all of your OHs and the CH2OH group is back here, So that's why it's relevant to learn about cyclohexanes. But no, I certainly will not say draw alpha, no, not until we actually cover carbohydrates next term. But there's a perfect example. glucose and other simple monosaccharides are just like cyclohexane, except we replace the CH2 with an oxygen. And so to understand one is to understand the other. Good, other questions then? And I guess I could leave it like that, but maybe I'll go back to presenter camera, because I kind of think we're done with the models for now. Good. So one thing that you might run into, and certainly I consider it part of the class material, it's in your book, but you sometimes run into this in lab also, is drawing cyclohexane using a Newman projection. And I want to sort of show you how that's done. Let me draw another chair down here. Actually, let me, I'm going to want some colors for this. And so what we're going to do with this Newman projection is we need actually kind of two parallel circles. Let me just draw in my bonds over here. I'll put in the hydrogens in a moment, but I want to color code these so that you guys can see what's going on. These I can leave as black. Let's now make these ones green. We'll make these red. We'll make these blue. And in the front there, we'll make them yellow. Hopefully that will work. Can't really see it. Maybe more like orange or yellow-orange. Good. So what we're doing here is we're actually looking down two carbon-carbon bonds at the same time. That's why I have two Newman projection circles. Now let me show you which carbon-carbon bonds we're looking down in this case. This is not the only way to do it, but we're looking down this bond over here, and we're also looking down that bond over there at the same time. And the reason we can do that is those bonds are parallel. That's always going to be the case in cyclohexane. So those two carbon-carbon bonds are parallel, those two are parallel. And also, those two are parallel. The ring consists of 3 pairs of parallel carbon-carbon bonds. And we could look down any one of those pairs of carbon-carbon bonds. I'm just, for the sake of argument, choosing to look down those two. So that means that we're going to have a CH2 group in back and also a CH2 group in the front. And that's these two CH2s, the ones that I've marked in black. So I should mention, one thing that's really necessary to understand cyclohexanes is you have to think in 3 dimensions. And a couple things, that's going to be even more so when we get to chapter 5. Thinking in 3 dimensions and being able to do that is one of those abilities that we all differ in. And some of us are born very talented with being able to turn things in 3 dimensions around in our heads. I was not one of those people, by the way, for what it's worth. I had to work really hard to develop skills in this area. Some people are just lucky. They're just born with great skills in that area. If that's you, then if you do, I mean, I would love it if you became like a surgeon. Ooh, that'd be great. If not something like that, then in my opinion, which doesn't really matter much, it would be great, I think, if you became like an architect. Because boy, I would never feel scared to drive across a bridge that you made. Be that as it may, you need to be able to think in 3 dimensions. This isn't going to be something you can master by memorizing a bunch of pictures. You need to understand what's going on. And so that involves getting with models, maybe. Someone asked about websites that maybe have modeling programs on them, so maybe you don't have to buy a modeling kit. I don't know of any off the top of my head, but I'm relatively certain things like that exist. And it might be that there's some website that would do you just as well as a modeling kit. If you find anything really great, by the way, please feel free to share it with me, and most especially with each other. Good, so we're looking down those two parallel carbon-carbon bonds. These green hydrogens are going to be in the front, so that's going to be these two. I also forgot to draw in some of the bonds. We've got a bond here and a bond here, and also a bond here and a bond there. Those are going to be the ones in back. And so these two hydrogens are going to be red. That's the CH2 in back. And then comes the blue one. These blue hydrogens are in back. And these yellow-orange hydrogens are in front. And I think you can see the angles all match. It's sometimes a useful way to draw cyclohexane chairs in terms of helping to figure out what's going on. It's not always necessary, but I mention it because, again, I'm pretty sure those of you in lab are going to run into that pretty soon. And so I wanted to at least mention that. Also, not to mention that it's in your book, but other than that, that's the main usefulness for these. And I think one thing that's really nice about the Newman projection of chair cyclohexane is, boy, it really is very clear now which positions are axial and which are equatorial. Except for there's two carbons that I really believe you should just write them as CH2s. And I would also recommend, this could come in handy for lab, if you're drawing substituted cyclohexanes, I would strongly suggest turning the molecule, however you may need to, such that the carbon in back and the carbon in front are just CH2s. They're unsubstituted. For me, at least, it's kind of difficult to show which is where the axial bond and where the equatorial bond is when it's coming right out at you or going directly back into the board, so to speak. That might be just me, but I would strongly suggest that you make life easy on yourself and turn the molecule so that you're able to do that and choose the bonds that you look down wisely. And in my experience, it's always possible to do that. I think you'll always find a way so that you can make the front carbon and the back carbon just plain CH2s. Just a suggestion as one who has been dealing with these for a while. Good. So the question was, were there brief questions? There were, but I believe if you register your attendance, it will still mark you as present and you'll still get those 8 points. So certainly do that. Maybe I'll switch to that. Should be able to switch to that. Yep. So it should take attendance also. So make sure it registers your attendance. I think that's all I really need to say about that. I want to spend our remaining 10 minutes on the issue of a monosubstituted cyclohexane, which is when things become a little bit more interesting yet. Any other questions? Any questions before we do that? Seeing if there's anything in chat. But yeah, this is something that you kind of have to get in there and practice, especially with models. No, I think it's kind of fun working with models. No, I think it's kind of fun. Maybe that's just me. Okay, so clear all drawings. Let's now consider a monosubstituted cyclohexane. And maybe I'll just make it methyl cyclohexane. So this also is going to have two different chair conformations. In one of them, the methyl group will be axial and the other it will be equatorial. We went over that before. We showed how when you do the ring flip interconversion, or ring flip conformational change, all axial groups become equatorial, all equatorial groups become axial. Or maybe I should say, the groups that had been axial become equatorial, the groups that had been equatorial become axial. And so, since, we can pick and choose, it doesn't really matter where we put our methyl group. All the positions are the same. So I think I'll start putting it there for no other reason than I feel like it. let's put in all of our 12 hydrogens. And maybe just for an extra treat, let's remember all of the remaining hydrogens. There we go. And then what about the equilibrium? Well, for now, I'll just draw the equilibrium arrow like this. We're going to wind up erasing that since we'll find that the equilibrium will heavily favor one side over the other. And so remember, and again, these numbers I'm using are arbitrary. You can number your carbons however you like. Maybe you even want to make that carbon 1 since the methyl group's attached. Doesn't really matter. I'm just putting in numbers as a visual aid so that you can see which carbons go where. And remember, we're going to grab this carbon and pull it up, and grab that carbon and pull it down, whatever they're numbered. We always just grab opposite carbons and pull one up and one down. The result is that the carbon we grabbed is going to appear to move up. And so what are we going to get as a result? Carbon 1 is just a CH2. Carbon 2 will look like this. Carbon 3, like that. The carbon I called 4 has the methyl group. So the methyl group had been equatorial. Now it's going to be axial. And again, this is also a CH2. And this one also a CH2. Let me just make that a little neater in spots. Oh, crap. Yes, so this one is 4 and that one is 5. Yep, there we go. So I would put it to you that those are the two possible conformations of this compound. It's only one way of drawing it. You know, you could have started out with the methyl group wherever you like. You can pick and choose. I don't want you to memorize that it goes there. That's a waste of your time. Just pick a spot. If it's a monosubstituted compound, just pick a place. Doesn't really matter. But when you do your ring flip, you want to make sure that you keep all your positions consistent. Certainly, one of them will have your substituent be axial and the other one will be equatorial, of necessity. Now, one thing I also want you to notice, I think you'll agree this methyl group is pointing down in this particular case, just because of how I've chosen to draw it. What about that methyl group? It may be hard to tell that that methyl group is down, but it is down. Again, if you're struggling with that, what I recommend you do is go back to the carbon that's attached to and find the axial group. And I think you'll agree that hydrogen is definitely up, no question. Can you all see what I mean? So if this hydrogen is up, then the methyl group must be down. So it goes from equatorial to axial when you do the ring flip chair conformation, but positions that are down, stay down. Positions that are up, stay up. That's one of the trickier bits about cyclohexane. And it will not be a terrible thing to let you guys stare at that a while over the weekend and practice a bit. But this is just one way of drawing the two conformations of methyl cyclohexane. And if it were any other group, it would be the same idea. Since we actually have more time than I thought we would, maybe I'll show you another way of drawing it with the methyl in a different position relative to our eyes. But I do want to cover one thing first, which is that now that we've drawn all this in, now that we've drawn all these things in, wait, 6, this is carbon 1, there we go. Now we can draw some conclusions about the relative energy of these. And it turns out that any non-hydrogen group is going to cause an increase in energy or a decrease in stability. Remember, higher energy is lower stability, lower energy is higher stability. But there is strain, and actually it's a kind of steric strain that you get when you have a non-hydrogen group in the axial position. And the reason for that is because all of the electrons in these CH bonds in the methyl group are going to be bumping into the electrons in these two CH bonds. Oh, wait a minute, what have I done? Got a little confused. This is fine. The other axial proton that's pointing down is over there. So let me actually go over those in another color so that you can see the other two axial hydrogens that are involved. One's there and one's there. And the reason I know that those are the two that are involved is because they're axial, they're pointing straight down, and they do have to be down to match the methyl group. So the reason I knew to look there is the methyl group's down, so I need to find the two hydrogens that are also down. And the electrons in those CH bonds are bumping into all of the electrons in all of these carbon-hydrogen bonds. So that's the problem. We call that, I think it would be better to call that steric strain, since I don't think that interaction is eclipsed, right? Eclipsed is to do with adjacent atoms, adjacent carbon atoms. These carbon atoms aren't adjacent. So I think steric strain is the better term to use there. But it's still, the main thing you need to know is it still involves repulsion of electrons in bonds leading to higher energy. Repulsion of electrons in bonds leading to higher energy. Both torsional and steric strain involve those. Torsional strain, though, seems to involve particularly eclipsed interactions, which these aren't. They're a little too far away to be eclipsed. But it still is something that can be measured, and these values are pretty well known. And I see with only 2 minutes left, I might not get to another one because I want to make sure that this point is clear. As a result, we're going to conclude that this conformation is higher energy, and this conformation is lower energy. It's more stable. And so if we were going to draw our equilibrium arrow and try to be careful to do it correctly, we would want to show that the equilibrium lies to the left in this case. Something like that, something equivalent to that. So as written, this equilibrium will have been an equilibrium constant less than 1, because the equilibrium lies to the left. We could just as easily flip around the equilibrium and make it stated the other way. There's no reason that the higher energy one has to go on the right. You could just as easily have drawn it in the other direction. Make sense? Well, I guess I still have a minute. Let me quickly scribble down another way of looking at the molecule. Maybe on this one, I'll put the methyl in an axial position. What about that axial position? And this way, if I use this lecture in the YouTube video, so far it has been not particularly disastrous. It's in the running to make it to YouTube. This way, this extra structure will also make it onto YouTube. And in this way, I think the equilibrium will lie to the right now. So I'm going to bend up, bend down. That means this carbon's going to go up here. Just let me make absolutely certain that I do this right. That means this carbon's going to wind up over here. Now my methyl group's going to be equatorial, and the other positions will all be hydrogens. So I think the ring flipped form will look like this. And honestly, I think that is a perfectly good place to end and enjoy our weekend. So on Monday, when we come back, we'll get to the issue of multi-substituted cyclohexanes. That's when things really get interesting. Got to consider cis and trans. So yeah, be sure you practice also knowing whether two groups on a ring are cis and trans. You can find that in the video of the last class, which again was pieced together from your class and the other one. Other than that, have a great weekend. We'll see you Monday.